My name is Audrey Sutt, and this is my Lab 5 report on Faraday's Law. To give you a brief introduction to the lab, the purpose of this lab is to collect observational data of a magnet falling through a conductive tube, then run the simulation computationally as well, and then compare the data sets that we found in between the two experiments. Some of the concepts reviewed are Faraday's law to calculate the current induced in each ring by the falling magnet, Newton's second law to calculate position or velocity updates of the magnet in the code, Newton's third law, which is to calculate force exerted on the magnet by the current carrying rings, and the Biot-Savart law to calculate the magnetic force exerted on each ring by the falling magnet. To give you a brief description into the real-life experiment, what we first had to do was determine the north end of the magnet using a magnometer app. Then we dropped the magnet through the aluminum foil tube and timed how long it took to fall through the tube, and then we repeated the step 5 times to be able to calculate the average time spent in the tube. This is some of the initial data for the tube and the magnet. The length of the tube was 0.3 meters, the width was 0.0087 meters, the inner radius was 0.16 meters. The mass of the magnet was 0.025 kilograms, and its mu was 1.35 amps meters squared, which was a value taken from our previous data from Lab 3. So these are some of the checkpoints that were established in the lab. The first question is, why can't we use a ferrous tube, for example, a steel pipe? A ferrous tube is magnetic and would disrupt the falling bar magnet and adjust its velocity. What happens to the magnet? How does this compare to a magnet falling in free space without a tube? Well, the magnet falls at a slower velocity in the tube compared to falling in free space because there is a magnetic force acting in the positive y direction that counteracts the gravitational force which acts in the negative y direction when falling through the tube. If a magnet were to fall in free space, then the velocity would be faster because there isn't that oppositional force and only the gravitational force acting on the magnet, assuming air resistance is negligible. So these were our real-life experiment results. As you can see, we ran 5 separate trials and were able to find the average of the bar magnet and its time spent in system, which was 1.26 seconds. So next we worked on the computational model. These 2 screenshots are to show setting up the initial conditions in the code for the tube and the magnet, and we use the data that we established previously for each part. These are 2 functions that set up and define 1, the magnetic field, and 2, the change in magnetic flux, and these functions will be useful later on in our calculations. So here we calculated the flux for a ring using the change in flux function found previously in the last slide. Then we calculated the current in a ring using the flux for a ring found earlier up above. Then we calculated the magnetic force on the ring and on the magnet, and we also calculated the magnitude of the magnetic force on the magnet. From there, we were able to calculate the net force using the magnitude of the magnetic force on the magnet and the gravitational force on the magnet, which is basically mass times the gravitational constant. So these were the results of our computational model. As you can see, the time spent in system was 0.767 seconds. Something to note is that as the magnet moves downward, the magnetic flux increases in the negative y direction. The blue circles are to represent the current flowing in the counterclockwise direction to counteract this increase in magnetic flux as according to Lenz's law. The red circles are to represent the current flowing in the clockwise direction. The difference in time spent in the system in the real-life simulation and the computational model is due to the mu that I calculated in Lab 3. When I was playing around with my code, I found that as I increased the mu, the time spent in system for the magnet computationally increased. So when we're interpreting the graph, as we can see, the magnet accelerates as it goes down, but then at some point, right before 0.1 seconds, it hits a constant velocity of about negative 0.4, indicating that there is a net force of 0 on the magnet in that time frame. Then it accelerates to the bottom. So these were some of the conclusion questions at the end of the lab. So the first one was, what if the resistivity of the conductor were reduced as close as possible to 0? How have the dynamics of the falling magnet changed? Well, if the resistivity of the conductor were reduced as close as possible to zero, according to Ohm's law, the induced currents would be larger, thus causing the magnet to fall slower. The second question is, what if holes or slots were cut into the tube? How would this affect the ring currents in your model? Well, if holes or slots were cut into the tube, the model would have less rings, and as a result, the magnet would fall faster because the magnetic force would decrease as with the induced current. Thank you very much for listening, and I hope you enjoyed my presentation.